Now we come to the second part of the student presentations. We had 2 yesterday, and we have 2 more today. And it's my pleasure to introduce as our first student speaker is John Fyffe. He's a PhD candidate advised by Chris Edwards, who we heard from earlier this afternoon, in the Department of Mechanical Engineering here at Stanford. His research in the Advanced Energy Systems Lab focuses on combining electrochemical energy conversion with the more traditional combustion systems, with the goal of achieving 70% efficiency at small scale. So John received his BA in Mechanical Engineering from the University of Texas at Austin, and he will be talking today on mixed combustion electrochemical energy conversion for high efficiency small scale engines.
Thank you. So it was nice. Chris talked a little bit earlier, so those of you who saw his presentation, that'll be helpful as we go through some of the stuff that I'm doing. So thanks, Chris. Okay, so today, like he already mentioned, we're going to be talking about our research into a new strategy using a mixed combustion and electrochemical energy conversion method to try to reach higher efficiencies. And so we're going to be specifically targeting smaller scale, whether that's transportation or distributed generation. So what that means is when you're thinking the technologies I'm using, think small scale turbines, so lower turbine inlet temperatures, all of those constraints, not grid scale devices. And so why do we want better chemical engines? Obviously, we talk a lot about wind and solar, but if you look at where energy comes from in the world, we're still at over 90% coming from some form of chemical fuel, and 80% of that is currently from fossil fuel uses. But a chemical engine could use a fuel that is bio-derived or even created using renewable energy, if you'd like, in the future. And so what do I mean by better energy systems? Well, today, that's going to mean more efficient. It could mean cheaper, it could mean lower emissions, but today we're going to just be talking about efficiency. And so if you look at the efficiency of systems over time, you'll notice about 100 years ago we were very inefficient. We had steam engines, and then technology developed, the efficiency improved, and then we had a step change as we shifted architectures. So that moved to steam turbines, and then gas turbine combined cycles, which is where we sit now. That's the current state of the art for natural gas-based systems. It's about 60% efficiency. And for coal, we have about 50% in the best case scenario. And so what we do in our lab is to try to figure out what are the things that we can do, the devices that we can use, the architectures we can develop to push past into the next energy system architecture. So what is this next line going to look at? And again, specifically, I'll be looking at what can we do on a smaller scale using the devices we have and the constraints that are currently in place. And so why are we using combustion and electrochemical energy conversion strategy? Well, Chris already talked a lot about engines and how they're very power dense. They accept a wide range of fuels, so it's a good starting point. And so let's look at an internal combustion engine. This is an energy analysis of an internal combustion engine. You have work that you can extract from your engine, so that's the blue bar. In this case, it's about 42% efficient. You also have some exhaust that's leaving the system. It's typically high temperature. That has some energy as well. And then you also have heat transfer, and that heat transfers to the walls, the piston, and the head, as Chris mentioned before. But another thing we can do besides just doing energy analysis of an engine is we can use an exergy analysis of the engine. And as Adam talked about earlier, exergy is the useful part of your resource, right? So it's the useful energy, the maximum amount of work you could extract from a resource. So it's a slightly different thermodynamic quantity. And this is an exergy analysis of an engine. And again, you'll see the work is about 42%. You still have the exhaust losses and the heat transfer losses, but you notice that big red bar that shows up on the top. And that is the exergy that you destroyed during the combustion event. It's not because you made hot gases and it transferred heat to the walls. It's literally from the process of converting your fuel reactants to the products of CO2 and water and your other minor species. So that's pretty bad. And so Chris mentioned the research that was previously done in our lab to try to make the most efficient internal combustion engine we could with the means that we already know and like technologies that we have available to us. So our goal here is to make this blue box bigger by making these other boxes smaller. It's a pretty simple approach when you break it down like this, which is nice. And so what we've done before is we reduced the heat transfer. So the yellow box, the heat transfer loss, got smaller, but then our green bar, the exhaust box, got bigger. Why is that? Our exhaust got hotter, right? So now we're just transferring hotter exhaust out into the environment. But we know that we can expand that through a gas turbine. We could overexpand our cylinder. And that would actually then improve our efficiency up to almost 50%. You can see our green bar is still pretty big. That's pretty hot gases still. We can do a bottoming cycle. And this puts us right around 60%. And this is kind of where we decided we've kind of hit the limit. And you'll notice that's because we have this big red bar that didn't really change over the course of all of these technological improvements, making it more of a combined cycle system. We still have this very large red box that's kind of offensive, and we want to reduce that somehow. And so one way you can do that is to use a fuel cell. A fuel cell takes hydrogen, typically, into your fuel cell and reacts it with oxygen through an electrochemical means. So you're not combusting it. It is a more restrained reaction. You still have the same kind of breakdown if you do an Xog analysis of it. You have some work that would come out of your fuel cell in the form of electricity. You would still have exhaust coming out of your fuel cell. And typically, most fuel cells cannot react all of their fuel, so you will have some remaining hydrogen coming out, which has high Xog value. So your exhaust, as you can see on the right, your exhaust Xog is quite large in this case. You're also going to have heat transfer out of your fuel cell. It's an exothermic reaction. And the most important thing to notice, and the reason why we are looking into fuel cells to build combined cycles, is our red bar. Our destruction term from the chemical reaction is very small. And so our efficiency might be 30%. You could design a system that's 40%. But the important part is that you're only destroying a fraction of your Xog, maybe 5% or less. And then the rest is transferred out of your system in the form of exhaust and heat transfer. And so if you don't do anything with those transfers, it's destroyed, right? If you just heat up like some cooling water and then dump that into the river, it's lost. If you don't do anything with your exhaust, that Xog is lost. But we can build a system around it and take advantage of these transfers. And so the important part here to compare against the engine is that the destruction term is small. We want to take use of the fact that it can efficiently convert chemical Xog into work while destroying very little Xog. And so that's what we're going to do. But like I said, most fuel cells require hydrogen. We don't have a hydrogen resource available, unfortunately, and so we have to produce it. Typically, you can use steam methane reforming to do that. There's many other ways you could do it. You could electrolyze things. But what we're going to do is we're going to use an engine that we know is very efficient at producing work, has very power-dense operation, and it can accept a wide range of fuel. So we're going to use an engine as a fuel reformer. And so instead of injecting the correct amount of fuel that would burn all of the fuel with all of the air that's in the engine already, we're going to put in about twice as much, roughly, fuel as normal. And what's going to happen? Well, you're going to partially combust your fuel. It's going to still be exothermic. And that reaction is going to essentially crack whatever fuel you put in there and produce a syngas. So it's going to be a combination of hydrogen, carbon monoxide, and other products. And it's going to be hot, which is perfect for us. So now we can pass that hot exhaust gas to a fuel cell. And here, just so you, for your reference, is an Xog analysis of such an engine. And you can see that we're not getting very much work out of our engine. That's as expected. We put a bunch of fuel in, and we didn't burn nearly all of it. But you'll also notice that our combustion destruction term, that big red box, got much smaller, by about a factor of 2. So we successfully didn't destroy this Xog, this 20% that we're used to, by doing a full combustion process. And you'll notice that most of our Xog is now in the form of our exhaust. So now I'm using that word kind of in jest because it's really high temperature hydrogen-containing gas. It's more of a fuel stream. So what happens when we build this system? We're going to take a jumping off point of that system that I talked about earlier, where we had an engine with low heat rejection, and we put turbo compounding on it, and we're going to use that as a base case. And we're going to say, OK, this is what we're comparing against, and this is what we need to kind of beat to see if we're actually going to have any luck with our strategy. And so this is what our system looks like when we had a first pass of this modeling case. And you'll notice that our destruction bar, that red on the top, is now only about 6%. Okay, so that's much lower than about 17% that we had before. But that's not the only thing you need to compare with. So we need to add up all of the reaction-related losses in our system to see if that is less than that 17%. Because if it's not, the strategy didn't really help us, right? Our goal was to reduce that reaction-related loss from 17 to something smaller so we could push past 60%. And so what happens is you look at it, that 6.4% is combustion, and then you have about 2% due to just your fuel cell destruction that I was talking about earlier, and you have another couple of percent that's lost in the fuel reforming process. So you can add some fuel downstream to the fuel cell, and the fuel cell will internally reform it. You could do it upstream, adds another point or two. But the important point is that now, if you add all those terms up, it's only at 11%. So we cut off about 6 percentage points. We reduced it by almost a half. And so now we can say, OK, that worked. We reduced that red bar. We reduced the reaction losses. And now let's proceed. Let's, again, go through this process of targeting the biggest losses and see where we could push this system, see how efficient we could make it. And the first thing that's easy to go after, that we have plenty of technologies and know how to do, is go after the heat transfer, right? We have hot, high-temperature exhaust gases. We can add a steam bottoming cycle. And now we're up over 60%. We're at 63.5%. So this is over 65% LHV system efficiency. And this is using small-scale technology constraints. Another thing we're thinking about is, where can we push this? How high can we go? So currently, this system that I'm showing you here has roughly equal splits of work production from your fuel cell, from your engine, and from your turbines, so your steam turbine and your gas turbines. But what if we push more of the energy conversion, the fuel conversion, to the fuel cell, just to see what happens? So we added more fuel downstream and shifted the work ratio to about 10 times the amount of work out of your fuel cell as the engine. And that bumped it up to about 69% exergy efficiency. So this is now over 70% LHV efficiency. And so in summary, again, our goal in the beginning was to see if we could reduce that combustion efficiency, the reaction-related losses, to push past 60% and maybe even reach 70% efficiency by using a mixed combustion and electrochemical energy conversion process. And we've shown that it is possible. One major thing that you'll notice is we kept adding these steam bottoming cycles. There's turbo compounding. There's a lot of thermal exergy in these systems because you're using high temperature fuel cells. You're using low heat rejection engines. And so managing these thermal exergy transfers in your system is critical. And that was something that Chris mentioned earlier, was talking about thermochemical recuperation, something that we're going to be exploring next. And so this is a very critical piece of the pie. And so really digging into, OK, are all of these thermal exergy transfers efficient and being done in the best way is kind of what we're focusing on now. And our preliminary results indicate that we can get over 70% LHV efficiency if we push this with relatively ambitious but not unrealistic parameters. And these are all using small-scale technological constraints by employing this mixed combustion electrochemical strategy. I'd like to acknowledge my colleagues that are working on the same project. So Mark Donahue, who had the poster yesterday that I think quite a bit of you talked to, and also Carol Ragabudo, my advisor Chris Edwards, and then everybody else in my lab who's great, and GCEP for their funding and support. And with that, I'd like to open it up for any discussion.
Efficiency compared to the 70% that you said?
Sure. So that system is 69% efficient. So we are 31% away from the thermodynamic limit, which is 100% exergy efficiency. So I know that sounds kind of silly, but there's no technical, other than just entropy, right? 100% is the definition of exergy efficiency, right? It's the maximum amount of work you could extract from a resource. So getting there, right, is probably impossible, but that's the limit. And so we're trying to push higher and higher.
So I must be missing something. See, you're having now two engines in the way you're describing this as working, an electric engine and your internal combustion engine?
So there will be electric generators. So the fuel cell will produce electric work, and then the engine and the turbines you could connect to electric generators.
If you were just using the electricity. But I mean, if
Right.
you were using it as motion. But why not just use a fuel cell?
That's a good question. So there's a couple of reasons to go after this kind of combined system. One reason is you have basically the engine acting as a fuel reformer. So if you don't have hydrogen to start with, then the engine is essentially functioning as your hydrogen generator while also producing work and increasing the temperature of that hydrogen stream. You can do that in other means. You can use steam reforming or other devices. But that's one reason. The other reason is you have somewhat of a synergistic effect of it is producing work. It is also potentially more rampable. So if you did have it in a car or even if you're doing distributed generation, fuel cells can't follow load clearly nearly as well. So you have that benefit. It's a side benefit, but something that we've thought about, if that helps. Thank you.
Okay, our second student presentation today is by Rebecca Belisle. Becky is a PhD student in the Materials Science and Engineering Department here at Stanford. She works with Professor Mike McGehee, developing novel solar cell technologies to meet the world's need for renewable energy solutions. And today, she'll be giving us a talk on understanding the role of device architecture in the success of perovskite solar cells. So let's welcome Becky.
Well, thank you to the GCEP organizers for giving me the opportunity to speak today, and thanks to all of you for sticking around to hear about the work that we've been doing in the McGee group to try to better understand the role of device architecture in achieving high efficiency in perovskite solar cells. So to get started, just to motivate why we're so excited about perovskite solar cells, perovskites, and in particular methylammonium triiodide, which is shown in the crystal structure here on my left, has been used in the past 5 years with extremely high efficiency in photovoltaic devices. So introduced in 2009 with efficiency around 5%, since then, with very few chemical modifications, it's now been used in devices with over 20% efficiency. And to put that into perspective, it took other thin film solar cell technologies like CIGS or cadmium telluride over 20 years to make those sorts of efficiency enhancements. So this rapid rise in efficiency has generated a lot of excitement in the field and has also generated a lot of questions. So in the community, we're interested in why these solar cells work so well, but even more than that, we want to know what can we do to push these efficiencies even higher. Now, as my title mentioned, I'm particularly interested in the role of device architecture in achieving this high efficiency. And when we say device architecture, we're really referring to everything besides the perovskite. So we like to think about solar cells as being defined by their absorber materials, but there are a variety of other semiconductors and metals that are important in achieving high efficiency. And in the case of perovskite solar cells, they have a PIN type structure, meaning that around the intrinsic absorber material, there's a P-type semiconductor and an N-type semiconductor that aid in hole and electron transport, respectively. So to sort of see how that works, we can look at an energy band diagram of our most basic perovskite solar cell, where the red is our wide bandgap N-type semiconductor. We have our intrinsic perovskite, and then we have a P-type semiconductor as well. For a solar cell to work well, obviously we need to absorb light and generate electrons and holes. We want to have a high current, so we want to extract these electrons and holes as efficiently as possible. And these selective contact materials, these highly doped P and N-type semiconductors, aid in that. As well as extracting charges, though, we obviously want to prevent them from recombining. If we can prevent non-radiative recombination, we can increase the VOC of our devices. And we want to increase efficiency, so high power, so high current, as well as high voltage are necessary. So recombination mechanisms that can happen in these devices are, of course, radiative recombination. So just an electron and hole recombining and emitting a photon. So the recombination mechanism that dominates, say, gallium arsenide technologies. But in our devices, they're made through a pretty messy process. So these are solution process multicrystalline thin films. So they have lots of defects in the material. And if these defects have energy states within our band gap, they can act as a trap in our material. So we can imagine a trap in the bulk of our material that could, say, accept an electron, and that electron may be stuck there until it recombines with a hole. So that would be a bulk trap-assisted recombination mechanism. We can also imagine other traps or defects in our devices that are particular to the surface of our material. And in that scenario, we could imagine we have an electron that becomes trapped at our hole transport material interface, and then recombines with a hole where there are many of them in our highly doped P-type semiconductor. What I'm going to talk about today is thinking about how the hole transport material, our P-type semiconductor, may affect these recombination mechanisms. So things you could imagine could be important when we consider recombination are things like the ionization potential of our hole transport material, which will effectively determine the energetic offset between the valence band of our perovskite and the valence band of our hole transport material. Secondly, we might consider the work function, which is going to describe how doped is our hole transport material based off of how close that work function is to our valence band of our HTM. And the question that we asked is, if we can understand the role of doping density, our work function, and our ionization potential of our hole transport material, can we use that knowledge to come up with design rules for our perovskite solar cells? So can we come up with design rules that will let us optimize the efficiency of these devices even further? So to begin to answer that question, we did a series of experiments and modeling to try to get at what's happening and then what can we do to improve our situation. On the experimental side, we know that the perovskites, their properties depend upon materials processing. So we looked at doing thin film characterization of materials that we made here at Stanford, as well as making devices with those perovskites and a range of hole transport materials. So hole transport materials that have varying ionization potential, varying doping density. We can then take all the information that we know and plug it into a 1D drift diffusion modeling program. So for this case, I'm using SCAPS, which is a numerical modeling program which calculates the Poissons and continuity equations, giving us our relative carrier concentrations for electrons and holes throughout our perovskite device. And although we know a lot about our system, we still have a variety of unknowns. In particular, we're unsure about our defect energy and the surface recombination velocity that we have. And those two things will affect our bulk recombination, our bulk trap-assisted recombination, I should say, as well as our surface recombination, as I mentioned. So we choose those as our Fyffe parameters, and we can generate a variety of solar cell characteristics and then compare our modeled behavior to our empirical data that we've previously collected. We do that until we get a best fit for these two parameters, and with that, we then look outward. So we say, if we can understand what's going on in the system that we've looked at, can we then say something about what would be the optimal hole transport material? And what we find is there's actually a range of hole transport materials that we could choose from that will allow us to optimize the VOC in our devices. So beginning with the experimental side, here are 3 representative IV curves for 3 different hole transport materials that we've used in our study. And these are representative of the types of experiments we would have done, where what we see is that by having a low ionization potential contact, represented by that black curve, we have in high doping, so this is a low ionization potential, meaning that we have a large energetic offset between the valence band of our perovskite and the valence band of our hole transport material, we achieve the highest VOC we see. If we say reduce the doping density as represented by that blue curve, or increase the the ionization potential of our hole transport material, our VOC drops in either case. Now we now see if we can recreate this trend of dropping VOC as we decrease doping density or increase ionization potential with our model. And what we find is we can't perfectly match the magnitude of the trends that we see with our experiment, but we can match the trends that we observe, meaning that as we drop the doping density of our whole transport material, or we increase the ionization potential, we see a drop in VOC in both cases, as well as matching the other sort of similar trends we see in IV characteristic. And we find that we can only describe this behavior by a model which considers recombination dominated by an electron trap in the bulk of our perovskite material. So to understand why a recombination mechanism and an electron trap would be dominant in these devices and manifest in the behavior that we've seen, we can again consider energy band diagrams. So in the upper right-hand corner, what you see is sort of that same picture of our simple PIN type device that I showed at the beginning of my talk. But in this case, we have an additional line, which is our green line, which is representative of our trap energy. And the things to pay attention to are our quasi-Fermi level positions of our electrons, which is that red line. And when it's above our trap energy, it means there's a high probability that all of our traps are occupied with electrons. Additionally, when that line approaches our conduction band, it means we have a high density of free electrons in our device. Conversely, when our blue line approaches the valence band in our material, we have a high density of free holes. Now, since I'm interested in particular what happens when we're changing the whole transport material on our perovskite, I'm going to be focusing our energy band diagrams at that interface. So first, we can consider our low ionization potential contact. So in this case, you see that there's an energetic offset between our valence band and our perovskite and our whole transport material. But the Fermi level for our electrons, which is that red line, is well above our trap energy at all times, meaning that all of our traps in our perovskite are full of electrons. Additionally, we see that that line is approaching our conduction band as we approach our whole transport material interface, meaning that we're accumulating electrons in this device. And we're accumulating them at a region where we have tons and tons of holes, right? Our highly doped P-type whole transport material. So we have increased recombination through that surface pathway. So in this case, we have increased surface recombination as we decrease our ionization potential any further or decrease the doping density. We can next consider a regime where we have higher ionization potential. So in this case, we no longer have that energetic offset, and we're no longer accumulating electrons at our whole transport material interface. However, in this case, we still have a high probability of all our traps being filled. Our quasi-Fermi level remains above our trap energy. So in this case, our recombination is going to be determined by the number of holes we have in our device. And it turns out the number of holes we have in the bulk of our material is increased as we increase the ionization potential of our whole transport material, and it's increased its doping density. We can imagine a third regime of high ionization potential and high doping, where we've now injected so many holes into the device by having such high ionization potential, so many holes in our whole transport material, that we begin to start to depopulate our traps. Now, in this case, we expect the VOC to again rise as our recombination is now going to be determined by the number of electrons that are in the bulk of the material, and increasing ionization potential will decrease that concentration. Now, this third regime is experimentally difficult to get to, but in any case, we find that our optimal whole transport material balances between these first two recombination mechanisms, where we are balancing between a surface recombination mechanism and a bulk recombination mechanism. Now, since we're looking at this in a model, we can consider a continuum instead of 3 discrete points, but we can again identify the same regimes. So first, on the left, when we have low ionization potential and low doping, we have accumulation of electrons and our VOC goes down. As we increase our ionization potential, increase our doping, we begin to accumulate holes in the bulk of our material, and again, our voltage drops. And we can identify a third, more extreme region where we begin to depopulate traps at very high ionization potential, very high doping. And in between this accumulation of electrons and accumulation of holes, we can identify a ridge where if we were to, say, choose a whole transport material whose properties exist upon that ridge, we'd be able to maximize our VOC by trading off between these two recombination mechanisms. So to conclude, the work we've done, I think, has identified a couple of things. One, in terms of advancing the knowledge of our system, sort of the perovskite that we're using, and the whole transport materials available to us, we find that our whole transport material allows us to choose between a bulk and surface recombination mechanism, and we can identify whole transport materials that exist along that ridge of sort of highest efficiency that we can choose and are now going to begin to implement in lab. The second thing we see, though, is that placement of that ridge is going to be dependent upon the materials properties of our perovskite. So depending on the relative intensity of, say, the bulk recombination mechanism, which you would imagine would be dependent upon the trap density in our film, or say the amount of surface that we have in our perovskite, there'll be a different magnitude of those two mechanisms, bulk recombination or surface recombination. And better understanding the perovskite will allow us to better predict optimal whole transport materials in the future. And just to wrap up, I'd like to thank my advisor, Professor Mike McGee, as well as the other members of the McGee group who continue to work on perovskites and help me with all the device fabrication. So with that, I'd welcome all your questions.
So I would think that an important trap would be the grain boundaries in the perovskite. Is that what you're kind of thinking?
Yeah, I think it's very likely that any sort of defect that we have is going to be in these grain boundaries. And there are people who have shown that the relative trap density we see in a thin film versus a single crystal differ by order of magnitude of about 10 to the 6 or so. So as we increase grain size, I imagine that we'd be able to reduce the trap density significantly.
But there's also, I think, some work done on adding a little excess lead iodide to the system as you synthesize it, which decreases recombination at the grain boundaries.
Yeah, so there's some, I would say, there's some work that suggests that, yeah, increasing the amount of lead iodide may actually serve as a passivant to those traps, but it appears that may not all be good news. So unfortunately, these devices also suffer from hysteresis, which is believed to be related to ion movement in the device. And it appears that having increased lead iodide, though passivating your grain boundaries may result in excess iodide that moves through your device and result in increased hysteresis and thereby affect your performance also.
Would you comment a little on the environmental,
Oh, hi.
Hi. Would you comment a little on the environmental and health concerns associated with perovskites, since these are quite toxic systems, as well as being water soluble, so they have a high potential for release into the environment?
Yeah, so absolutely. So I think the thing you're referring to is that obviously these perovskites contain lead, and they're also a water-soluble compound. So there's significant concern of sort of incorporating them at a commercial scale. I think the sort of points about that is that there are ways of encapsulation that are potentially engineering challenges that a variety of people are pursuing, and there are people pursuing this commercially in the UK. So they think that they can address it, and that perhaps the UK consumers are okay with it. The second thing is the actual amount of lead that's actually in these films. So I'm not entirely sure what the number is, but in terms of a panel of PV, the amount of lead that you would expect to be there is relatively low, right? These are 100 nanometers of this material over a large area. So I think the idea is that potentially that there's a trade-off in terms of the energy benefit that you can get, and then also obviously concern in how do we encapsulate better, how do we make sure that none of this lead is leaching out, how can we manufacture them in a safe way.
Did you do any work to measure the carrier lifetime to relate it to the material property?
Yes, so we've done a lot of work looking at particularly how if we change processing conditions, we can change the carrier lifetime in our devices. So for instance, for the processing condition that we use for these devices, the lifetime is on the order of 60 nanoseconds, but by changing the processing, we can increase those lifetimes up to hundreds of nanoseconds.
So what is the factor which change the carrier lifetime in your case?
So if we change the carrier lifetime, it's a little complicated because you have to assume that change is could somewhat be related to surface recombination, somewhat related to the bulk recombination. But effectively, as we turn off non-radiative recombination pathways, which would increase our radiative recombination, increase our PL lifetime, we see all of the VOCs go up. All right, thank you so much.